Hi everyone, this video is on dividing radicals. And typically when we divide radicals, what we really want to talk about is rationalizing the denominator. Or if you hear, rationalize the expression. What that really means is that we do not want any radicals to appear in the denominator. Alright, so at the end of our problem, if we have to simplify to get rid of radicals in our denominator, here we're going to learn how to do that. And we'll do it through some examples. So in this example, if I said to simplify, and we'll start with a fairly basic one. We'll say if I have 2 over the square root of 7. So the issue here is the square root of 7 in the denominator. We can't have a square root down there. Now the idea is that you want to multiply the denominator by something to force the inside to become a perfect power of the index. So that's kind of a general way of saying it. In this case, since we have a square root, what I really want to do is multiply by something to make this a perfect square in the denominator. Now the easiest way to do that for a square root is if you multiply it by itself. Because if I took the square root of 7 and I multiplied by the square root of 7, right, that's going to give me the square root of 7 squared, or the square root of 49. So over here, I'll write our new fraction. The square root of 7 times the square root of 7 would be the square root of 7 squared. But if you do this to the denominator, you also have to do it to the numerator. This is what keeps our fraction balanced. So I have to multiply the numerator by the square root of 7. So 2 times the square root of 7, well, that's just 2 square root of 7. And then what you want to do is simplify the denominator. Really simplify the numerator as well if you could, but square root of 7 does not have any perfect square factors. So we keep this as 2 square root of 7 over, down here, the square root of 7 squared. Well, remember, when you have a power and a root that match in terms of the index, you divide it out. 2 divided by 2, that's just going to give me 7 in the denominator. So we got 2 square root of 7 all over 7. And that'll be your answer. In other words, the square root of 7 squared down here, right, that's going to be the square root of 49. The square root of 49 is 7. Notice the square root is gone though. The reason is because we have a perfect power, 2, of the index here. So 2 divided by 2 gives us, 7 to the power of 1. And now if 2 and 7 here reduced as the coefficients, you can reduce them, but square root of 7 is going to stay here in this problem because you can't simplify that any further. Don't try to cancel these. Let's take a look at another one. If I had the square root of x over y. Notice the square root's over the entire fraction, so the first thing you really want to do is rewrite this as the square root of x over the square root of y. And now you want to simplify. Now to simplify this, remember, I want to rationalize. I don't want any square roots in the denominator. Square roots in the numerator are okay, but square root in the denominator is not. So how can I make this look like a perfect power of 2 here? Well, really the goal is to make this y squared inside of the root. You want to multiply this by the square root of y, because you multiply the square root of y times itself, it's the square root of y squared, right? So you multiply it by itself, that'll make this a perfect square. If you do it in the denominator, you also have to do it in the numerator. So the square root of x times the square root of y is the square root of, now since these are both under the same root with the same index, you can multiply them as the square root of xy. And then we want to simplify this. The square root of xy, if that simplifies, you'd simplify. In this case, it doesn't, so you keep it as square root xy. Over the square root of y squared, remember the square root of something squared is just whatever the base is, so in this case it's just y. In other words, the index of 2 on the root, and you have the power of 2, so the power of 2 divided by the index, 2 divided by 2 makes that y to the first power. And then make sure if you can simplify here or not. You can't simplify this. Remember, this y is under the radical, this one isn't, so they're not the same factors. So you leave it like that, and now we've rationalized. Let's take a look at another one here. If I was to put, say, y over 2 square root of 5. Remember the goal. The goal is to rationalize, meaning having no radicals in the denominator. So the issue here is that square root of 5, not the 2. Although you could work with the 2 if you wanted to. So I want to come up with a fraction that doesn't have any radicals in the denominator. Well, the 2 is okay, but how do I make square root of 5 look like the square root of a perfect square. Well, I really want to make this a 5 squared inside of the radical, so I have to multiply by the square root of 5, because when you multiply together, you get 5 times 5, you square root of 25, or just the square root of 5 squared. Whatever you do in the denominator, you have to do in the numerator as well. So in the denominator, 2 in front will stay 2. Square root of 5 times square root of 5, you know, if you can just remember this, right, the square root of something times itself is just the base. It'll be just 2 times 5. I kind of did a little shortcut there. You could write the square root of 25 here if you wanted to, or the square root of 5 squared, but it's going to come out to 5 either way. Make sure you know the 2 is still in front. So you got 2 times 5. In the numerator, y times square root of 5. Since the y is not underneath the square root, keep it in front, so it's y square root 5. And then we'll simplify here. Square root of 5 doesn't have any perfect square factors other than 1, so we keep it as y square root of 5. In the denominator, you have 2 times 5, which would be 10. And then making sure you understand these can't cancel because this 5 is underneath the root. The y and the 10 don't cancel at all because they don't have any common factors, so you just leave it like that. And we've rationalized, right? There's no root in the denominator. Sometimes a common mistake people make, and it's not really a mistake, but it just makes it more complicated, is they multiply by the exact same denominator they see, and that's not always the case. You saw it here and you saw it here, but that was only because those were exact square roots that you wanted to make perfect squares. Here, if you have a coefficient, the coefficient doesn't need to get multiplied through. If you did multiply by 2 root 5, you'd have to do it up here, and eventually it would cancel out in the end and still get to the same answer. Let's take a look at this one. Maybe I'll do it on a new page, just so you can see. We're going to do this problem 2 different ways, just to get to the same answer, just to see what happens. So if I had this problem here, if I said I had 3n over the square root of 18n. What you might want to do first is recognize that the square root of 18n does have a perfect square factor in there. And if you have a perfect square factor in here, you might want to simplify the denominator first. So the square root of 18n, perfect square factors, non-perfect square factors, remember how we simplify. Square root of 18 is not a perfect square, but it has a perfect square factor of 9 times a non-perfect square factor of 2. And then n, well, that doesn't have a perfect square factor. Since the index here, 1 is less than 2, that's going to be the non-perfect piece. Remember, the power has to be a power of 2 in order to make it perfect. We can't get 1 out of this. The 3n in the numerator stays 3n. And so we'll simplify here, and we end up with 3n over the square root of 9, which is 3 times the square root of 2n. At this point, since 3 is a coefficient for both of these and it appears in the numerator and denominator, you can cancel it out because it's being multiplied too. So you end up with n over the square root of 2n. And then now we want to simplify this. Well, the square root of 2n, to rationalize, remember you have to multiply by whatever would make this a perfect square. So what I'm going to multiply by, right, to make this perfect square, is the square root of 2n. If I do that in the denominator, square root of 2n times square root of 2n, the square root of something times itself always gives you what's on the inside, so it's just going to be 2n. If you do it in the denominator, though, you have to also multiply by that same thing in the numerator. N times the square root of 2n is just going to be n square root 2n. And then you may recognize here that these n's can cancel now because they're both outside of the root, so those n's will cancel out. You can't cancel this 2 with this 2 because this 2 is inside of the root. So this ends up being the square root of 2n all over 2. And then you have it there. Now let's say you didn't recognize you could simplify that square root of 18n in the denominator. Well, you might want to try approaching this as, okay, you have 3n over the square root of 18n. And let's say you're just like, I want to get rid of the radical right away. Well, if you wanted to do that, right, you have to multiply by, to make this a perfect square, you might just notice you multiply by the square root of itself. So multiply by the square root of 18n here. And then if you do it in the denominator, you have to also do it in the numerator. Now remember why we did it. In the denominator, the square root of something times itself just gives you whatever was on the inside, the 18n. Right? It's really because it becomes the square root of 18n and the quantity squared, and then when you take the square root, you just get the base. Here in the numerator, you got 3n times the square root of 18n, and I'll just write it like that. 3n times the square root of 18n. Now remember, you always want to simplify completely. In this case, the 3 and the 18, they're both coefficients in front being multiplied through, so you can cancel 3 divided by 3 would give you 1, 18 divided by 3 would give you a 6. N here and n here will cancel because they're both outside of the root. And then you're left with this. You have 1 times the square root of 18n, which is the square root of 18n over 6. Simplifying this now, don't forget to look. If the square root on the inside has a perfect square factor, you have to factor this. So the square root of 18n actually does have a perfect square factor, so you can factor this as perfect squares and non-perfect squares. The square root of 18n, well, we did this earlier. Square root of 18, the highest perfect square factor is 9. The non-perfect factor would be 2. And then we have n here, which isn't a perfect square factor and it doesn't have any perfect square factor, so it goes in the non-perfect piece. And this is all over 6. Simplifying this, the square root of 9 give us 3 times the square root of 2n, all over 6. And then, now that the 3 is on the outside here, 3 and 6 share a common factor of 3. This 3 divided by 3 gives you 1. 6 divided by 3 will give me 2. End up with the square root of 2n over 2, which is the same answer we got the other way. So it really has to do with personal preference if you want to simplify first, like we did up here, or if you want to actually, rationalize first and then simplify at the end. Either way, you should get the same answer. Let's talk about what happens when you have higher powers. So when you have a square root, it was easy enough just to multiply by the exact same root you saw. Because you multiply a square root by itself, the base on the inside becomes a perfect square. But if the power is higher, you really want to talk about what would make it a perfect power of the index. So for this example here, if I said to simplify, and we'll start with, if I said I had 5 over the cube root of 2. Now when you do this, you can't just multiply by the cube root of 2, because that would just give you the cube root of 2 times the cube root of 2 would be the cube root of 4, and that's not a perfect cube. What you really want to do is you want to say, okay, I have this 2 to the first power. I want to make it look like 2 to the third power, right, because that's my index. What do I have to multiply to make this look like the cube root of 2 to the third power? Well, if I have the cube root of 2 to the first power, you would multiply by the cube root of 2 to the second power, and then 1 plus 2 will give you 3 as the power. So you're really kind of trying to make the powers add up to whatever the index is, or at least something that's divisible by the index. If I do it in the denominator, I have to also multiply it to the numerator, so times the cube root of 2 squared here. Well, what does that give us? Well, if I multiply 5 times the cube root of 2 squared, the cube root of 2 squared is the cube root of 4, so I'll simplify that. 2 squared is 4. Down here I didn't simplify it because I want you to see it's a perfect cube. You could call this 2 to the third power the cube root of 8, but the idea is that I want you to understand that what you're really trying to do is make this index be divisible by, or make this power be divisible by this index. So simplifying this, we have 5 cube root of 4 over the cube root of 2 cubed. Remember, 3 divided by 3 here, the power divided by the root, will give us just the base of 2. And so we've rationalized it now. Now if you made this into an 8, the cube root of 8 is still 2. So you get the same thing. So we have 5 cube root of 4 over 2. Does the cube root of 4 have any perfect cube factors other than 1? The answer is no. 5 and 2 don't reduce here because they don't have any common factors other than 1. So that's it. So what we did here, which people find to be a little more challenging after what we did in the first examples, was when you have a cube root, right, you're trying to make this look like a perfect cube, make this power look like 3. So you have to think about what you have to multiply by to make this a perfect cube. When we have a square root, you multiply it by itself because anything times itself gives you a power of 2, which is the index of a square root. So paying attention to the index really matters. How about this one? If I said I had the fourth root of 7 over 5x to the third power. First thing I would notice here is that this root's over everything, but you really want to separate it out. You want to make this the fourth root of 7 over the fourth root of 5x to the third power. And now you want to rationalize the denominator. To rationalize this, remember your goal. Your goal is to make this denominator a perfect fourth power because the index is 4. So we have the fourth root of, now I have 5 here. I want to make it look like 5 to the fourth power. And I have x to the third here, but I want to make it look like x to the fourth power. The goal is to do this, so then we'll divide by the index to get just the actual base. So what do you multiply by here? Well, we have to multiply by, it has to be under the same root, so the fourth root. Now I have 5 to the first power here. I want to make it look like 5 to the fourth, so what I really need is 5 to the third power. And I have x to the third power. I want to make it look like x to the fourth, so what do I need? Well, 3 plus 1 more, so just x to the first power will give me 4. Now, whatever I do to the denominator, that's what I multiply to the numerator. So this is the fourth root of 5 to the third power times x. So simplifying this, when I multiply this, I have the fourth root of 7 times the fourth root of 5 to the third isn't a perfect fourth power, so you can actually raise that power. 5 to the third is going to be 125, and then you have x here. And now we want to simplify. To simplify this, in the numerator, these are both fourth roots, so you can multiply them together underneath a single root. So the fourth root of 7 times 125, you do 7 times 125 here, you get 875. So the fourth root of 875 over down here. Now remember, these are fourth powers, and you're taking the fourth root. So the power divides by the root, and you just get the base. So this is going to end up being 5x. Now, if you didn't notice that and you did 5 to the fourth power, you get 625. Taking the fourth root, you go back to 5. But it's important to write it like this because it makes it easier to see, right? It's easier to work with. The last thing you have to do is determine, does this fourth root of 875 simplify any further? The answer here is no, because there aren't any perfect fourth powers that are factors of 875. And I just noticed I lost my x. There should be an x there, right? It's the fourth root of 875x over 5x. But it still does not have any perfect fourth powers, so that's our answer, and it's rationalized. Let's just take a look at a couple more. You might want to pause the video and try it on your own here. If I looked at the 12y squared over the fifth root of y to the third power. So you might want to pause this and try it on your own. First thing I noticed, I want to rationalize, get that root out of the denominator. To do that, I need to make this look like a perfect fifth power on the inside. Well, I have y to the third. I want to make it look like the fifth root of y to the fifth. So what do I have to multiply this by? Well, you multiply by, you have y to the third. How many more do you need? You need 2 more, so this is multiplying by the fifth root of y squared. So when you multiply, you add the exponents. Whatever you do down in the denominator, you had to do in the numerator, so this will be times the fifth root of y squared up here. And when you multiply these, remember, you're just writing this coefficient, 12y squared, next to this, so times the fifth root of y to the second power. And now we'll simplify. We have 12y squared, fifth root of y squared. That doesn't simplify. Remember, if your power is less than your index, you can't reduce that any further. Over the fifth root of y to the fifth. The reason we did this is because 5 divided by 5 will just give me y here. And then if it simplifies it all, you should simplify it. You have a factor of y squared and a factor of y here, so the factor of y will cancel with one of the y's in the y squared, so that'll be a y up top. And you're left with 12y fifth root of y squared. This is really over 1. Anything over 1 is just itself, so it's really 12y times the fifth root of y squared. Let's just take a look at a couple more. If I was to look at this one here, let's say, if I had the cube root of 2 over 3x squared. So first thing I notice is that it's a cube root of the entire thing, so I really want to make this a cube root of the numerator over the cube root of the denominator. Right? So the cube root of 2 over the cube root of 3x squared. And then what I want to do is really simplify this down to a perfect cube inside of the cube root in the denominator. Remember, the numerator doesn't matter when you rationalize the denominator. So I need the cube root of, well, think about what I want. I want this 3 to be something to the third power, so I'll call this 3 to the third here, and I want x squared to be something in the third power, so I want this to become x to the third. And then you just have to ask yourself, okay, what do I multiply this by to get to 3 to the third x to the third? Well, you multiply by the cube root of, well, if I have 3 to the first power, I need how many more 3's? Well, I have 1, I need 2 more, so it's supposed to be 3 squared. All right, so 3 to the second power. And I have x squared, I need to get to x to the third, so I just need one single x to the first power to get to x to the third. Whatever I multiply the denominator by, I multiply the numerator by the same thing. So times the cube root of 3 squared x. Simplifying this, this will give me the cube root of 2 times the cube root of 3 squared, which is 9x. And then we're going to simplify this. Simplifying this here, I end up with the cube root of 2 times the cube root of 9x. Since they have the same index, I can write this as the cube root of multiplying the insides together. 2 times 9x gives me 18x over the cube root of 3 to the third x. So remember, the power divides by the index. That's why we did this. So 3 divided by 3 gives us 3 to the first power, which is 3x to the third. 3 divided by 3 is x to the first, so over 3x. And then if this simplifies any further, you simplify it further, but does 18 have any perfect cube factors? Well, remember what your perfect cubes are, right? Starting with 1, the next one would be 8, right? And then the next one would be 3 cubed, which is 27. So the cube root of 18 doesn't have any factors of 8, and that's really all you could look for here. So this is simplified. You can't do anything else with it. The cube root of 18x over 3x. Let's take a look at a different type of example here. So remember, you're always simplifying at the end if you can. If I said to simplify this one here, if I said I had the cube root of x squared over 4z. First thing I notice is that I want to take the cube root of the numerator, which is x squared, over the cube root of the denominator, which is 4z. And you want to ask yourself, okay, how can I make the inside of this look like a perfect cube? Now, in all the previous examples, I said, what would it take to make this 4 to the third power? And you could do that. But if you notice 4 is the same as 2 squared, which is something you might see in my math lab if you were to do a problem like this in there, you really want to make this like the cube root of 2 to the third. So if you already have a power in here, you might want to use it because it keeps your numbers smaller. So instead of using this as 4 and calling this 2 squared, I really want to make this 2 to the third. And this is z, and I want to make it look like z to the third. So it's really no different than what we've been doing, except for now I'm saying 4 is already a perfect power, so it'd be 2 squared. Well, what do you multiply by, right, to make 2 squared look like 2 to the third? Well, you need the cube root of 2, because you have 2 of them here, you need one more, so 2 to the third. To get z to look like z to the third, you want to multiply by z squared. Whatever you do in the denominator, you've got to do in the numerator. So this is the cube root of 2z squared here. And you can multiply these together, the cube roots, since they have the same index, you can multiply them together, and this is the cube root of 2x squared z squared, just multiplying them together. And now we'll simplify. So we have the cube root of 2x squared z squared. There are no perfect cubes in here. 2 doesn't have any perfect cube factors other than 1. X squared and z squared. Since the power is less than the index, you can't get any perfect cube factors out of that. Over down here, the cube root of 2 to the third is just going to be 2. The cube root of z to the third is going to be z. And you end up with 2z. So cube root of 2x squared z squared over 2z, and that's it. Nothing will cancel, because remember, these are inside of the radical. This one isn't. So if you didn't do this, where you turned 4 into 2 squared, you would have probably multiplied by 4 squared and made this 4 to the third. But that would have changed what happened up here. You would have had to have simplified the numerator, because you would have had a perfect cube factor in there. So it's helpful to notice this, but you can still get to the correct answer. It just needs to be simplified more. Alright, so if you have something that's already a power in there, it's helpful to write it as a power so then you just know how many more pieces you need to get to the perfect power you need. Let's talk about what if you had two terms in the denominator. So here's a note. If the denominator is a binomial, and contains a radical. Binomial, meaning two terms, and contains a radical. We rationalize by multiplying by the conjugate of the denominator to both the numerator and denominator. Right, just like when you multiplied earlier, both the numerator and denominator when you were rationalizing, you do this because it keeps the expression balanced. If you only did it to the denominator, then you would not be keeping the same expression. Because it's like multiplying by 1. When we say conjugate, remember what that means. You're just using the opposite sign between the same term. So if I have a plus b, you'd multiply by a minus b. If I had a minus b, multiply by a plus b. So I'm going to pause it just to write that down. Taking a look at an example here. If I said to simplify something like this, if I had 2 over 3 plus the square root of 5. So first thing to notice is that you have a radical in the denominator and you have two terms. So that's what's telling you that you want to multiply by the conjugate, right? You can't just do what we did above in the earlier examples where you just multiply by the square root of 5 because now there's more than one term. If it was only one term, if there was no addition or subtraction, then you could. But here we have 3 plus square root of 5. I want to multiply this by its conjugate, which would be 3 minus the square root of 5. Remember, you're just multiplying by the opposite sign. And whenever you do in the denominator of fraction, you have to also do the numerator to keep it balanced. So it's going to multiply by 3 minus square root of 5 up in the numerator as well. Now, when you do this multiplication in the numerator, I would recommend just keeping the coefficient out in front as 2 times 3 minus square root of 5. If you don't, you leave the 2 and distribute it in, that's fine. You'll probably have to factor it out at the end, though, if you are trying to see if it simplifies. You got 2 times 3 minus square root of 5 over the denominator. Now remember, when you multiply something by its conjugate, we talked about it in the last section, you just multiply the first, so 3 times 3 would give you 9. And the last terms, because you multiply by the conjugate, the middle terms cancel out, so you don't have to do the full steps of FOIL. So 3 times 3 gives me 9. Positive square root of 5 times negative square root of 5 gives me a negative, because a positive times a negative is a negative. Square root of 5 times square root of 5, remember the square root of something times itself, is just going to give you whatever is on the inside. So this is really the square root of 5 squared, or the square root of 25, which is just 5. Right? It's always whatever's on the inside when you multiply the square root times itself. Now we'll simplify. I'll keep this as 2 times 3 minus square root of 5 for now. Over here, 9 minus 5 is 4. And since we factored out this 2, you could recognize that 2 and 4 share a common factor of 2 that divides out. 4 divided by 2 is 2. 2 divided by 2 gives us a 1. So you have 1 times 3 minus square root of 5, which is just 3 minus square root of 5. This whole thing is over 2. If you had distributed 2 in initially after this first step, you would have had to have factored it out in order to cancel here. So 3 minus square root of 5 over 2, and that's the final answer. It doesn't simplify at all. Square roots in the numerator are okay. It's the denominator where they give us issues. Let's take a look at a couple more. If I said I had 7 over the square root of a plus 5. So again, first thing I noticed, I have a radical in the denominator, so I want to rationalize because I have two terms here. I want to multiply by the conjugate to both the numerator and denominator, so I'm going to multiply by the square root of a minus 5. Whatever I do to the denominator, I also have to do to the numerator. And so I have 7, I'm going to keep in front, times the square root of a minus 5. Keep it as a coefficient for now. In the denominator, remember when you multiply by a conjugate, you always multiply the first and the last. And that's why that, this takes care of those square roots, because you're always going to get a perfect square when you multiply something by itself. So square root of a times square root of a is the square root of a squared, or just a, right? The square root of something times itself is just whatever the base was in the inside, so it's just a. And then we have a positive 5 times a negative 5, so positive times negative is a negative. Remember, 5 times 5 now is 25. It's not a square root, so you don't leave it as 5, right? If you multiply a whole number times a whole number, it stays that whole number. It gives you a whole number, I should say. It doesn't keep the same value, right? 5 times a negative 5 is a negative 25. You multiply as normal. Once you're here, you simplify if possible. In this case, can you simplify? Well, you can't simplify between the square root of a minus 5 and the a minus 25. They're not the same factors. You can't cancel 5s here because these are different factors. Remember that a is married to that 25 by that minus sign. You have to have the exact same factor in order to cancel in the numerator. So you're left here with just this, really. You could distribute the 7 in now because there's really nothing else to do with it. 7 square root of a. 7 times the negative 5 is minus 35 all over a minus 25. And then paying attention here, you got to be kind of careful. Can you simplify this? The answer is still no. The 35 and the 25 can't be simplified. The a's can't be simplified. Remember, this is an entire factor. They're married together by that minus sign. You can't cancel any of this unless you do the exact same factor in the numerator. So you can't cancel term by term. Remember, that's the rule about when you have fractions. You only can cancel the same factors from the numerator and denominator, not the same terms. Meaning things are being multiplied is what you would need up here. Let's just take a look at one more. If I had the square root of 14 minus the square root of 11 over the square root of 14 plus the square root of 11. So first thing to notice, these look very similar in the numerator and denominator. Can you cancel the square root of 14s or the square root of 11s? The answer is no, because they're not factors, right? They're terms, and you can't cancel terms, you can cancel factors. So if you only can cancel factors, then we're ready to just do what we normally do. I see radicals in the denominator. I'm going to multiply by the conjugate of the denominator. So the square root of 14 minus the square root of 11. Whatever I do in the denominator, I also have to do to the numerator. So multiply the square root of 14 minus the square root of 11. Now, when I do this, make sure you put parentheses around these because you are multiplying the whole thing. You might notice I've been doing it. You need the parentheses or it's not the same operation. The other thing is be very careful in your numerator here. Are these conjugates? No, they're not. Remember, you multiply by the conjugate of the denominator. If these aren't conjugates, you have to actually FOIL the entire thing. You can't just multiply the first and the last. Right? Only conjugates have that special property because the middle terms cancel. So multiplying these together, square root of 14 times square root of 14, well, square root of something times itself is just the inside, so 14. Square root of 14 times a negative square root of 11. So I know it's going to be negative if you wanted to multiply those together. 14 times 11. You get minus, now it's the square root of that, so minus the square root of 154. Here you've got a negative 11 times the square root of 14. Well, it's going to be a negative, again, square root of something times the square root of something else. You can multiply them together under one square root. 11 times 14, again, is 154. And then negative times a negative will make this a positive. Square root of 11 times the square root of 11. The square root of something times itself is always the inside, so plus just 11. Or you could write the square root of 121, which gives you 11. Over. In the denominator, are these conjugates? Well, yes, they are, right? One has a positive in the middle, one has a negative, so you can just multiply the first and the last. Multiplying the first, square root of 14 times square root of 14. Remember, square root times itself just gives you the inside, so just 14. The last, because remember the middle terms cancel, square root of 11 times a negative square root of 11 will give me a minus, and then square root of 11 times square root of 11 is just 11, right? Just gives you whatever's on the inside. Can you cancel the 14s and these 11s? The answer is no, right? Because these are not factors, these are terms. In other words, they're not being multiplying, they're being added and subtracted. So you want to combine like terms in the numerator and denominator. 14 plus the 11 will give me 25. Negative square root of 154 minus square root of 154. These don't cancel. Be very careful here. Right? This is really minus 1 square root of 154 minus another 1 makes it minus 2 square root of 154. They're like radicals, in other words. over the denominator 14 minus 11 cancels to 3. And then you should ask yourself, does this simplify any further? The square root of 154, does it have any perfect square factors? It might be tough to figure out, but think about where it came from. It came from 14 times 11. The factors of 14 are 7 and 2, or 1 and 14. The factors of 11 are just 1 and 11. So since none of those factors repeat, then there's no perfect square inside of here. In other words, there's no factor times itself. So that 2 square root of 154 won't simplify any further. You can leave it just like this, and that'll be your final answer. So it's important to practice this. You know, it's something that people get tripped up on if the index changes on your roots. But remembering, you know, if you're looking at something that has two terms, you know, you're really typically going to be having the square roots in there. If you have something that just has one term in the denominator, you're trying to force the denominator to have the same power as the root. This way you can cancel it out. So hopefully you can practice this and work on some examples that are similar, and let me know if you have any questions.